A todos, gracias por estar en esta sesión de los seminarios, del ciclo de seminarios del Departamento de Recursos Naturales del Instituto de Geofísica. Soy el doctor Manuel Alberto Hernández, miembro del comité organizador. Todos los que nos siguen por las redes del instituto, agradecemos su presencia. En esta ocasión nos acompaña el doctor Fabrice Papa, que nos hará una presentación de su trabajo. Y antes de darle la palabra, la presentación será en inglés, vamos a hacer una breve lectura de su biografía. Dr. Fabrice Papa is a hydroclimatologist. He's the director of research at IRD, Institute of Research for the Development in France. Works at Lagos in Toulouse. His research focuses on the study of the water cycle, continental hydrology, and Earth's climate in the context of global change. He is particularly interested in the characterization of continental freshwater dynamics in tropical regions, such as Amazon, Congo, Ganges, and other rivers, in order to quantify the impact of climate variability and anthropogenic pressure on the water resources. He has more than 20 years of experience in the development of integrated methodological approaches based on Earth observation techniques, in situ observations, and hydrological modeling. More recently, he is interested in the interactions of continental hydrology with the ocean and vulnerability of population to extreme events. Much of his work is resolutely multidisciplinary, is carried out in partnership with South America, in countries like Brazil, Colombia, and Chile, Africa, and India. He is a member of the science team for the NASA and CNES satellite mission, Surface Water and Ocean Topography, SWOT, and co-leads the SWOT River Science Working Group. He's also in charge of the SWOT of South America initiative and for organizing the South American Water from Space Conference Series. His talk will be the hydrodynamic variability of large tropical river basins from space, current advances, and future opportunities. Go ahead, Dr. Fabrice. Thank you.
So thank you very much for the introduction, and I will do my talk in English. So it's a real pleasure actually to give this lecture today, a small talk about my research. And so as you said, I'm a French researcher working for IRD, normally in Toulouse. But my institute aims at developing collaboration worldwide. And I'm lucky enough, I've been posted in Brazil for the past 5 years at the University of Brasilia, where I've been working since 2019 with my colleague from Brazil. And I'm very grateful to Miss Raquela Herrera, who I met last year in Florianopolis during a workshop from the IAHS initiative for Latin America. And we started to discuss after I made the presentation of our group. And later on this year, I've been contacted by Miss Nelly Ramirez Cerrato, who invited me to give this talk today. So thank you very much for the opportunity. And as you introduced it, my talk will deal with the hydroclimatic variability of large tropical river basins using space observation, and what we know currently from the use of this space observation, and what are the future opportunities. As you will see, we have been entering an era of new satellite observation dedicated to hydrology, and this opens many new aspects. Okay, sorry. Yes. So the major topic of my research, as it has been introduced, is water. And water, it's a major scientific and societal issue. So we all know that fresh water is a vital resource, but it's very limited. And I like this small sketch, actually, where if we would take over all the liquid water on Earth and put it in a sphere, it would represent like the first sphere, which is about like the United States and Mexico, which with the diameter above just 1,500 kilometers. And from this, if we would extract the fresh water, it would be the second smallest sphere, which with a diameter of only 300 kilometers. And from this fresh water, what is available to the human in this very, very small sphere, which is above Florida. And this tells us like how important it is actually, the fresh water as a resource for humanity. Moreover, the continental water, the one which are present on the continent, they are less than 1% of the total amount of water on Earth. Therefore, but they play a critical role in the continental water cycle and the climate system. So continental water, they are critical for the life, human health, the activity, and our environment. Moreover, they play a key role in the global water cycle, in the energy cycle, in the carbon cycle, and more generally in the climate system and how it varies. All this brings that water resources, which is a component of this water, is very important for the governance and the society. So here are the two major questions that could resume the work that we are doing in my group and then I'm animated with for the past 20 years, is how this water resource, this water availability is, how these water resources are available on the continent and how do they vary with time and space at different scales, from the local scale to the global scale. And also how do they interact with both the climate and all the recent human activities. We are putting pressure we are putting a lot of pressure on the water resource. These questions, of course, are very important at the global scale, but they become even more critical for the intertropical region. They are very relevant, in particular, for large tropical river basins, such as the two major river basins, the Congo, namely, and the Amazon, but other tropical river basins, such as the one we find in Southeast Asia. Why? Because these large basins, they play a key role in the global water cycle, but also in the biodiversity. They are generally covered with large rainforests and tropical forests. And over the last decades, they've been highly impacted by human action. So the Amazon, for instance, is very well known for deforestation, for putting dams that are breaking the flow of rivers, and also mining. And on top of this comes the vulnerability to climate change. Therefore, as we've seen very recently, they have become more and more vulnerable to what we call extreme events. And both extreme events, floods and drought. And we are now getting into a paradigm, which is like, might be the future of the Amazon basin, for instance, is that while the wet gets wetter, the dry gets drier. So among the seasonal cycle, which is already very large, we get this extreme event, extreme floods, which can be followed the year after by a very extreme drought. Therefore, if we want to follow the Sustainable Development Goal, where water is a key parameter of this SDG, we need to understand and forecast freshwater resources, their availability, and how they change globally. So this is the fundamental question that is animated my research. So observing the water cycle has been done for decades, if not centuries, actually. And traditionally, we do that by making in-situ measurement, by deploying networks, such as the key parameter that we all know is measuring soil moisture, groundwater when it's possible, water level. And from that, we derive a key parameter, which is river discharge. However, while there was a good amount of observation globally, so these figures show the distribution of the amount of discharge measurement available on the global database, which is GRDC, the Global Runoff Database Center. And you see that there was a peak in the 1980s. And since then, for the past 30 years, there is a constant decline on the number of gauges which are available globally to measure the flow of and stream of all the rivers in the world. Especially, so there is a declining in-situ network, and often these measurements, when they are made, they are often not available for science and technology development. You know, water is a precious resource, and there are many states we are reluctant in sharing the the data that they have on their water resource. Moreover, we have become to an era where actually also measuring certain parameters which are key to the global water cycle are very difficult. For instance, this is a picture of a floodplain in the Amazon, and you can imagine that measuring the extent of water, the flow of water in this kind of environment, which is most of the time also very remote. So it's very, very difficult to do that using traditional in situ measurements. Therefore, as a complement, not as a substitute, but as a complement of in situ measurement, there is for the last decade the advent of hydrology from space, meaning like observing the water cycle and its major components, such as soil moisture, such as water extent, water level. We will see all this in detail later. They are measured from space-borne satellites. And we can try to characterize at different space and time scales this variable using a satellite. So we can go from using different variables in the spectrum that can measure water quality, also water quantity, and the variability and the change of these different variables. This is two figures that I extracted from a recent review paper that is going to be published soon, which is dealing with the potential of hydrogeodesy. So hydrogeodesy is a certain part of the hydrology from space that encompass altimetry, INSAR, gravimetry, GNSS, and all these measurements combined. And the first figure on the left shows the progression or the time series of the number of papers published in the 90s. And you see that there is a constant increase in the number of publications every year for the past decades that use this space technique to study the water cycle and the related science. And the figure on the right shows the use of these different techniques, so gravimetry, GNSS, INSAR, altimetry, that have been published in the last decade regarding to the parameters we are looking at. So for instance, altimetry has been widely used to monitor lakes and ice. A little bit more river, but less wetland. For INSAR, a lot has been used on ice and rivers, gravimetry, a lot to measure terrestrial water storage. We will see it using a GRACE or at the watershed scale or the groundwater, and GNSS has been used widely, but recently for all this. So what we can conclude from that, for instance, is that wetlands, which is a key parameter of the hydrology, especially regarding the carbon cycle, didn't attract as much attention as the other parameter, but it will change probably with the launch of, we will see the satellite SWOT or the future launch of the satellite NISAR. So just to give a first example of what we just talked, like we all know that, for instance, GRACE, which has been launched in 2002, provides now for more than 20 years the variation of the total water storage, which is like the amount of water on the continent that is varying month to month. And this is a famous paper that I extracted that provides the first trends which are emerging from the availability of global fresh water. And you can see that depending on the region in the world, there are some negative trends, some positive trends. One of the largest example is in Africa or over India, where there are groundwater depletion, most of the time due to the use of groundwater for agriculture. So space hydrology, the hydrology from space, we have published a paper 2 years ago that really showed that the Amazon was a natural laboratory for the development of remote sensing for hydrology. And in this paper, we review more than 3 decades of the advances that has been done in terms of science regarding Amazon hydrology and the water cycle using satellites. So this is a very interesting paper that has been published by one of my colleagues from Brazil, Alice Cesar Fassoli Andrade. And in this paper, we review all the quantities that we have gained. This is the goal of this figure, and that we have discovered or revealed using satellite over the last 20 years. And what we show in this paper is twofold, is that satellite has been really useful to discover more on the science of the Amazon, but the Amazon was also very useful for the development of the satellite technology and how to retrieve certain parameters. So there's really like a twofold, two-way exchange between the Amazon and satellite, that they gain each other in the knowledge. So for instance, here I will show just like, for instance, the precipitation, they characterize how much precipitation using all the sensors over the Amazon, the evapotranspiration. We are covering in this review most of all the parameters, hydrological parameters, which are which the knowledge has been increased using satellites. And in particular, there are three of them, which are the key of my research. Is the surface water elevation of the Amazon. So how much the river are fluctuating with the wetland every year, and how do they change? The floodplain inundation and their extent. The river discharge, which is the flow of the Amazon that goes into the Atlantic Ocean. More than about 20% of the total amount of fresh water that is flowing into the global ocean every year is coming from the Amazon. And also the changes in the terrestrial water storage and how all the compartments of this terrestrial water storage, which are the surface water storage, the water which is stored in the lake, in the floodplain, and the wetlands, the root zone saltwater, and the groundwater, how do they contribute to these changes? So I will basically try to talk a little bit of the techniques that have been developed to measure these three compartments. So one of the key instruments of which my lab and the CNES, the French Space Agency, is leader is radar altimetry. So thanks to radar altimetry, we can measure the variation of the water level from space of freshwater bodies. You all know that primarily altimeter was developed to walk over the ocean. You know, these famous maps that shows the trend of sea level rise globally linked to climate change. They are most of the time made with the several altimetry missions. Altimetry measures sea surface height variation over now more than 30 years. But very rapidly in the 19th, they have been used also to measure the variation of the water level of freshwater bodies, such as first rivers and lakes. So they are used to estimate this water level variability with a repeat cycle, which is given by the orbit of the satellite. So what we have from the past 3 decades is repeating altimeter with a cycle of 10 days to 35 days, with intermediate repeat cycle of 27, 29 days. And so what we measure is the water surface variation at the cross between the altimetric track and the water body. And this location on the river basin is called a virtual station. So in regard to a station, a ghost station that provides water level, we have defined what we call virtual stations that provide water level elevation from the satellite. So the figure at the bottom right provides the various missions of altimetry, mainly of classical altimetry, that have been launched since the 1990s, with the most famous being ERS, Topex Poseidon, the family of JSON, Saralaltica, and now the new family from the European Space Agency, the Sentinel family, Sentinel-3, AB, and now Sentinel-6. So you see that there are many missions which are covering the same span since more than 3 decades. We will come back on that later. So just to make a little example of what is a virtual station. So you see the top left figure. This is an image like from Google Earth over the Amazon. And in the rectangle, you see all these little dots. So this is the instantaneous measurement that have been made by the altimetric along its track. So a classical altimetry, it's not imager. It's going along the track and is making the measurement by measuring the delay between the radar wave between the surface and the satellite. And with this, we can reconstruct the variation of the height of the water. And you see on the right, so this is the water level that we gave over the Amazon in red from JSON 3, as compared to in situ measurement, which are in blue. So the measurement of water level from altimetry has improved largely over the past 30 years. In the beginning, for the missions like TOPEX or ERS, the uncertainty were between 50 and 100 centimeters, 1 meter. And now, with the new techniques that have been developed, both for the algorithm, but also from the technique itself, because now we use like a SAR image from altimetry, we are now, as shown on the figure below, uncertainties which are less than 10 centimeters long. So we are somewhat something which is very close to what has been measured with the gauge. And this is, for instance, a time series. I extracted this from the Congo River, not on the Amazon. But you see that when you merge all the different missions, you can go now to have like long-term observation of the same target of the same river with an accuracy which is something like here less than 26 centimeters over more than 25 years. So there are many publications where this is well explained and well shown. So this is what you get in terms of virtual station over the Amazon basin. You know, the Amazon basin is huge, it's remote, and it's very difficult to maintain in situ network there. Nevertheless, Brazil has many agencies who are capable of doing this, such as the ANA or SGB. But over the Amazon, in terms of water level, for instance, there is at the maximum 100 stations working, and they need to cover 7 million square kilometers. So you see that as a complement, altimetry can bring many virtual stations. And this is, every dot here is a location, a virtual station, where we can measure the water level evolution over the river basin. So you see that here is displayed on the left is the median amplitude of the elevation, which is shown. And you can see that in the Amazon, the rivers can sometimes fluctuate in 1 year more than 10 to 15 meters. Of course, in situ measurement normally are made every 15 minutes, every hour, every day. So this is why I say it's very complementary, because this one, they cover a large spatial geographical area, but they probably provide between 10 and 30 days of sampling. And then when you combine both, you can really go and understand the processes. And this is just the two figures on the right are just to show when the water level is maximum and when it is minimum during the year. So this is the month. And you can see really the fluctuation between the northern part and the southern part of the basin. And this is a very nice one because it shows different contribution during the season to the flow of the Amazon. So there are many papers, again, I said that evaluate altimetry versus in situ, and that show the complementarity of this technique. So this is other example, because I'm going to show that altimetry has also the power of being global. So this is over Africa. This is extracted from a publication we did like a couple of years ago. That shows the amount of virtual station that you can have over Africa, and especially on the panel C, over the Congo basin. So the Congo is even worse than the Amazon. Congo has now 6 stations. It is almost 5 million square kilometers. And there is only 6 stations which are measuring water level and discharge over the Congo. So you see, like here, the altimetry provides a clear advantage because you can cover. And now over the Congo, we have 2,500 virtual stations. And some of them are completely automatic. I will see that then later. And then, so that provides really another way of seeing the variability, the hydrological variability of a river basin. This is just to show some example that now also, why altimetry was devoted until about 10 years ago to very large river, because the signal was not properly understood, or because the altimeter feature didn't let us do that for smaller river. Now, with the new development, if the altimetric is passing through a river on the track, there are techniques from algorithms that can extract water level for rivers which are as narrow as 100 meters. So you can see here that you can have water level over the Congo, of course, very big river, but also very smaller streams such as the Bani, the Lurio, for instance. So this is becoming increasingly better and better, and this is very promising for altimetry. At a global scale, this is just to show this is the amount of virtual stations that we can have that can cover globally the information that you can get on rivers for many basins worldwide. So this shows the maximal amplitude that has been observed from altimetry. So you can see now over the large tropical basin, you have like some of the largest amplitude, more than 10 meters. But then you see that you can also measure or at least depict like this amplitude for many river basins in the northern latitude, in the tropic and intertropical zone as well. So these data are freely available. So most of the altimetry data, they are put on several websites. So there is a website which has been moved recently. So now it is called HydroWed Next. It is something that will be developed at Lagos with the French Space Agency and many other partners in France. And then you can register freely, and you can have access to all the data which are on the website. So you see like the number here, for instance, for the Amazon means how many stations you can get over the Amazon. It is much more now. I should update this figure, but you see there are like now about 15,000 targets globally, targets that provide water level elevation for a certain period. And there is a subset of this which is providing long term also. So that goes from 93 to now. And so there are some stations where you can get, for instance here, long-term time series when you combine all the different missions. So now, as on the previous website, a lot of detection are done automatically. And we have to be careful because they can have errors. And especially there are still difficulties to intercalibrate the various missions. When you want to create a very long-term time series, you need to be very careful because it's difficult to calibrate the different satellites. Nevertheless, with the expert view and working really nicely on the station, you can get now time series which are 30 years long and that you can use for many applications. So here, for instance, is in Parintins, it's in the Amazon. And there we combine all the satellites that were available and that we intercalibrate with in situ measurement by doing like GNSS survey. And so we combine TOPEX, CRS, and this, so many to obtain like this this long-term time series. And I just want to here note that this is in terms of water level. And we are working now towards deriving this water level into discharge. So altimetry, if you calibrate the satellite, it can provide complete like long-term time series of river discharge. But this I won't talk too much today. So altimetry is very powerful for hydroclimatology because now we have 30 years plus time series. and the data are secure for the next decade. NASA and ESA, for instance, they have agreed on continuing like the Copernicus program. So Europe probably has altimetry mission up to 2040, 45 now. So you see that it's been secure for another 20 years. And when you have long-term time series, they become important tool to study extremes. For instance, here in the Amazon, you probably know that in 2005, there was a very major drought in the Amazon. And while they have been depicted by in-situ measurement, that was the first time that using altimetry, we can map the strength and the spread of the drought in 2005. So you can see that the water level were 5 to 6 meters below in October 2005, below the average. So this was one of the first times we could show the mapping of this. And unfortunately, the largest drought in the Amazon occurred last year in September, October, November 2023. And this was major. This was massive, like as you can see, like again, the water level were 5 to 6 meters below the average. And the map here shows like the anomaly of the minimum recorded. So every year for the past 14 years, we've been recording the minimum of the year. And this is the anomaly in 2023. So you see that in some places in the Amazon, when the Amazon is already low, the water level were even lower than ever recorded, 5 to 6 meters sometimes. So you see that altimetry can become a very powerful tool. We put altimetry on the side. There is another parameter which is very important for hydrology is the inundation and the floodplain and the extent. So I will go a little bit faster on this. But I just want to show that there are many techniques from spaceborne data that can help to map the extent of water. Of course, one of the very famous one is the use of SAR over the Amazon. So in the top left image, that's the SAR from Laura Hess that's been published in 2003 and 2015. But then there are many other techniques that have been developed. Here I show just one, for instance, is GIMS, which is a global scale estimation of flooding, merging different data sets. And you can see that while they compare regionally, the various techniques, they have difficulties in finding the same extent everywhere. And this is shown here. So there was a question that we were wondering in the last few years, how much actually the Amazon is inundated. So we started to gather all the data sets that estimate the extent of water over the Amazon. And we ended up with 58 data sets, which is huge. 30 that cover the full Amazon and another 28 that cover local estimates. And so we started to make this agreement map for 30 data sets globally in between all the data sets. And then they cover very small scale, fine resolution, lower resolution, and they are extracted from SAR, they're extracted from passive microwave, from optical. So we merge here all the maps that have been developed over the Amazon. And what we saw is quite shocking actually, is that most of them, they never agree actually. So of course you have a big agreement on the open water, which is good. But the Amazon is not only water, open water. Most of it is under flooded forest. Most of it is in flooded savanna. And there, all the data sets that have been developed, they really disagree. Like, and especially for the interfluvial wetlands, which are key for the Amazon, because they are very important for the carbon cycle, for the biodiversity. This one are not really well depicted. And so there is a message to do is that even the biggest river basin in the world, we still don't know exactly how much inundation happens year after year in this basin. We have a sense for some, but there's still a lot of research that needs to be done. So now I'm just going to go to quickly through examples. So why these data are very important? So as you see me, I'm very interested in water level, water extent. And these data, they have been key actually for the development of hydrological models. So I won't be too much into detail, but you know that for hydrological model, we need to calibrate them, to validate them, and we can also do assimilation. And altimetry and the data from the surface extent has been very, very important in the last 20 years, in parallel to the increase of computational capacity to develop models. And now we are capable in the Amazon to do reanalysis for hydrology for over 100 years. We're capable of doing very good projection for including climate change. And this is done because the satellites have been very helpful to understand the processes and also to develop hydrological models. For here, I just give an example from the one from my colleague in Porto Alegre, which is a model which is called MGB, for Modelo de Grandes Bacias. And so it's a very powerful tool as a complement to also in situ and satellite. Using all this data, you can also understand the processes and the changes. And the hydrological cycle of the Amazon is changing a lot. And it's very striking because in the common sense, we all think that the Amazon is drying because of deforestation. And that's what we saw before. It's been hit by extreme drought in the last 20 years. But superimposed to this drought, there is a lot of new flooding happening in the Amazon. And if you look over the last 40 years, when you look at models and satellite observation, the inundation in the Amazon that happen every year, they have increased by about a quarter, 25%. And this is seen is not only the change in the extent, but also the flood duration. And this has a lot of implications. For instance, that will modify the connectivity between the rivers and the floodplain. And you know that floodplain and river are very important to exchange nutrients, to exchange carbon and water. And all this, therefore, this increase of extreme events and of larger inundation over all the Amazon has a lot of implications for the ecosystem, for the carbon cycle, as I said, but also for the local population. There is more and more population which needs to migrate in the Amazon for both reasons, because sometimes they are too isolated from the river because of extreme drought, but sometimes they are too often flooded, and so the crop cannot grow, and then so they need to migrate like this. And all this, the reason for that is a combination of many aspects. Of course, human intervention, but also large-scale climate footprint, such as the modification in the Walker cell that has changed the way precipitation been increased on the northern Amazon. And all this resulted in this change over the hydrological cycle of the Amazon, which is just the beginning. And this I wanted to show you because for geophysics is very important, is by combining all the data that I showed up to now, and especially by combining GRACE data that measure total water storage, by combining extent and water level height, we can try to calculate the amount of water which is stored in different compartments of the hydrological cycle over the continent. So basically what we did, I'm not going to go too much into the details, but there is a very unknown stuff, is how much the groundwater is varying in large river basins. So we have tried to decompose and use all this data to decompose the signal from GRACE into the hydrological component of GRACE, which is the surface water. So how much water is stored and varying in the river and in the floodplain? How much water is stored in the soil moisture and vegetation? And if you subtract this from the change of GRACE, which measure the full component, you might have a sense of the variation of the groundwater. So really something that we don't see. So it's a technique that we have published like a few years ago. And an interesting stuff is that over the Amazon, So if you take the grade changes, which are linked to the total water storage change, 45% of this change is due to surface water. So the water which is stored annually in the floodplain, in the rivers, they contribute to almost half of the change from grade. 25% is in the soil moisture, and 30% is due to the change in the water in the aquifer. And therefore, for the first time, we have tried to map the spatial variation of the groundwater over the Amazon from satellite. And so the top map shows the groundwater storage change annually and the standard deviation, the variability. So this has been done for 8 years, from 2003 to 2010. And this is a map, and it really shows that actually, where you have the largest aquifer, such as the Alter do Chão, in downstream Amazon, you record the largest changes. So what is interesting is that, for the first time, we could map the variability of the groundwater storage over such a large basin from a satellite, and which is a little bit an unknown, which is difficult to assess because there is almost no observation of how groundwater is changing in this area. So all this that I show up to now has been done with mainly only satellites which were not done for hydrology. We use satellites that have been developed for ocean and everything to do hydrology, but for the last 20 years, the scientists and the agency, they have planned the SWAT mission, which has been launched now in December 2022. And one of the primary goals of SWAT is to take a look at surface hydrology. So to provide a global inventory of surface water, lake, reservoir, wetlands, and rivers above 100 meters. And from many years, try to estimate how much water are stored in the lakes, in the river, and how much discharge is happening everywhere. So this satellite has been launched recently. It is part of, you see, all the family of altimetry. So you see that there are many of which are still planned to be launched, in particular Sentinel-60, which will be another SWAT altimetry. So just to go quickly, so SWAT is a SWAT altimeter. It's not a nadir altimeter. So it's not making observation only at the nadir along the track. It's making images of 100 kilometers like this, approximately. And it's done through a K-band radar interferometer, which has a 100-meter spatial resolution. And the full cycle of SWAT is 21 days. But because of the SWAT, it's passing at least twice by the same location. So every 11 days, at minimum, you have an image of the current surface globally. So SWAT makes map of the extent, the height, and the derivative of this, which after that you can convert into parameters such as water storage and discharge. So this is just to illustrate. It was one of the first images of SWAT released by NASA in New Jersey that shows the mask of SWAT. So you can see that you really depict the water very well, even tiny, tiny little fractions of water. Here is another one of the hometown of SWAT, Toulouse, which is a city in the southwest of France. And you can see that there is a large river in Toulouse, but there is also a little stream, which is like 20 meters wide, and SWAT can see it. It's here somewhere. It's very impressive. So the carrying instrument is very, very powerful one. And in the frame of SWAT, and this is how I met your colleague from Mexico last year in Brazil, we have an activity or a group which is called South America Water from Space. So about 10 years ago, we started to develop in South America an initiative of people who are interested in hydrology from space. And we call it South America Water from Space, and which is around many projects funded through France, Brazil, Colombia. And in particular, we have a team which has been selected to do the calibration and validation of the SWAT team in Brazil. But this is an example of a device on the photo. So we're going to the Amazon and we have GPS and we have many instruments and we are making measurements concomitant to SWOT. Alors here is a carpet. You see we call it the geodetic carpet. So in pink, it's a carpet, floating carpet on which we install GPS on it, and then we track it all over the rivers to get precise measurement of the elevation of the river. So we have been covered like many places in Brazil, downtown Amazon, here like in the Rio Negro, which is like at the border between Colombia, Venezuela, and Brazil. And for many weeks, we have been doing like this kind of measurement for the carnival of SWOT. And so SWOT has been launched in December 2022. For about 6 months, there are data available on the NASA and the CNES website. So this is a few examples of what you can get over Brazil. So water elevation on all the streams, floodplain on the Kuruai, for instance, to study the river floodplain hydrology, and branching rivers over the Rio Negro. So they are still, as you can see here, they are still being checked, validated. There's been a release of the data for the public, but there's going to be a huge reprocessing soon. So the people who are in the science team are working a lot with the data, and we find good stuff, many bad stuff. It's a very complex instrument. So for instance, here, this is the difference on top in red, all the dots. This is the difference that we obtain between SWOT and from our GNSS on the little device on the floodplain. And you see that it is quite good, but there are some slopes that we don't understand. When you go too far from the nadir, they start to have some problems. You know, and let's see, like we have few years to develop this instrument, and I'm sure it's going to be, once we have made all the correction and we understand the signal, it's going to be very, very powerful. This is another example over the Rio Negro. So you see that over all the points, like this is the difference in meter between our ground measurement and the satellite, and we are within like 10 to 20 centimeters for a long stretch of a river. And this has been done during the fast sampling phase when we had measurements from the satellite every day. So if you're interested in the data over Brazil, we have a regional augmented website for altimetry in the Amazon, and you can visualize all the virtualization that we have. We will put the institute data, we'll put the SWOT data soon, but then you can already see, this is an example when you go on the drought last year, you can get, and you have all the anomaly, and in red, negative anomaly, and you can visualize the time series, the actual time series of the year as compared to the mean, to the maximum ever recorded, to the minimum before. And so it's very useful, and you can go in this website. So for the moment, you cannot download the data. You can request if you want. Download it. We need a little bit more time because of the bot, and then otherwise it's going to cause problem to our website, but we are working on it. Finally, in this group that we have in South America, we are organizing conferences every 2-3 years that gather all the scientists which are interested in working with satellite, hydrology, water cycle, climate. So we did 2 in Rio, 1 in Santiago de Chile in 2018, 1 in Manaus. There was a very big one in Foz do Iguaçu in 2022. And this year, we will host another large conference that will happen in Belém. So Belém is in the Amazon region. It's not the Amazon basin, but it's the Amazon region. It's north of Brazil. And from the 29th of October to the 2nd of November, we will have this conference with 3 days of talk, poster, dealing with SWOT, with altimetry, with many of these satellite applications for precipitation and all the processes of hydrology. And then on the last day, we will have courses. So people are doing courses on how to create virtualization, how to use SWOT data, how to use models. So hopefully some of your institute will be interested and to join us. And it's a very good opportunity to create a larger group. We were 150 last time in Foz do Iguaçu, maybe even larger this time. For instance, there will be a course on how to use a SWOT product. You see, it's very complex. You can go for very complex radar expert measurement to some which are a little bit more easier to handle. And so there will be courses on how to use, for special cases, how to use this SWOT measurement. They will be done by people from the French Space Agency. And maybe NASA will travel to Berlin to provide the course. This is just because you know the first article I was talking, the reviews of geophysics on the Amazon from space. We decided that it was important that not only in English, so we decided to translate and make a book. So we translated it in 2 languages. It's very important for South America, one in Portuguese. This has been done and has been released last year. And we are working now on the version in Spanish. So it's a very nice book. Yeah, all the chapters are actually a sample of the paper we publish on the AGU. And you can get this book if you want on the AGU website too. And hopefully soon in Spanish, we have the funds to do that. People started to work. My Spanish is very poor, I'm sorry. And so I don't work on the translation, but hopefully some people will like to read this in Spanish. So I'm done. Thank you very much. Thanks.
We thank Dr. Fabrice Papa for this presentation. And now we will give some time for questions. And for instance, Alessandra, you raised your hand, so go ahead. Maybe she's not available.
Hi.
Carolina, ¿cómo dejamos que abran su audio?
Catalina no está, doctor. Yo estoy acá y estoy viendo si... Listo. Ya solicité para que reactive el audio. Alessandra puede hablar cuando quiera. Nada más sin activar su micrófono y listo.
I'm sorry, I didn't hear the question, or I didn't understand the question. Sorry.
Yes, Fabrice, we are waiting for Alessandra to do the question, since she's not able to open the micro. Alessandra, can you write it on the chat, your question? Well, while we wait, I have something on the chat. Nelly said, thank you very much for your time. I really enjoyed your presentation. Will there be an option for online streaming for the event in Brazil?
Yes, so I send a reply in the chat. Yes, normally we are broadcasting like most of the session online. So our partner, which is the Geological Survey of Brazil, LGB, has a channel, YouTube channel or anything on the web, on the social network, and they broadcast fully the conference. So
Great.
I don't have fully the decision now, but normally it will be done. If you want to check, like on our website, you can find the recording on the LGB website, all the recordings from the previous event, and you can see how it is. Like it's very well made. It's on the YouTube channel normally, and then so you can follow the event like that.
Great, thank you. I have another question from Dr. Roberto Avila. He says, can SWOT be applied in arid climate basins and measure reservoir levels?
Oh, yes, yes. Actually, to measure reservoir level, it can be applied anywhere globally. And of course, it works also in arid climate. So for that, they have defined a mask, which is called the PLD, which is the Reservoir and Lake A Priori database. And from that, they extract water level and water storage from all the reservoirs, which are larger than 200 meters. And there are many projects using SWOT, which are dedicated to water level monitoring in reservoir, especially in Brazil. That I know, you know, there is this arid, semi-arid region in Brazil, which is called Ceará. But many of my colleagues are working also in Africa, in the Sahel region. There are many reservoirs, and you can look on the website of SWOT. Many of the use of SWOT is for reservoir. So in northern latitude, in a temperate latitude, but also in arid reservoir, in arid climate. So yes, it's a very powerful thing. And if you want more insight, I can put you in contact with one of my colleagues, which she's an expert of that, and she's really working on using SWOT data for this purpose.
Thank you. Just for clarifying, the maximum extent of the river that the SWOT mission can measure, can you give us an additional explanation? Maximum and minimum?
The minimum. Like so, if you want to make the distinction between the water and land properly, the goal of the mission is river which are largest than 100 meters. But you know, this is the goal of the mission, and then there are the practice. And what we can see is that the pixel cloud of SWOT, which is like the raw measurement from the SAR, is going to provide measurement below that. So it is going to be possible to have a river which is smaller as 50 meters, maybe 40 meters. And from that, we can extract the water level. So for the mission itself to be successful, the maximum resolution, let's say, is 250 meters for the lakes and reservoir, and 100 meters from the rivers. If they can achieve this goal, the mission works in terms of what we say, like the mission specifics. But you know, like the same, the altimetry, the specific were only the ocean, and 20 years later, we are doing like rivers of 100 meters too. So let's see what all the development of SWOT in the next few years will bring. We are pretty confident actually that it's going to be a powerful tool for that too.
Great. Dr. Graciela raised her hand. So if you're able to speak.
Yes, I am able, yes, to use my microphone. So hi, Fabrice.
Hi.
Thank you very much. Hello. Thank you very much for the talk.
You're welcome.
I think, well, it was very interesting, and these are very, very useful tools, I think in general, but also for countries like Mexico and some other Latin American countries in which typically we don't have so much data measured directly, and these other sources of information are very important. And I think that there are many opportunities to use what you are generating in SWOT in Mexico, in projects in Mexico. So I think there are many opportunities to do some work together. I mean, we would be interested in doing that. So thank you very much.
Yeah, sure. Thank you. Yes, as I said, you know me, I'm not a specialist of arid environment, of reservoir. but I'm willing to cooperate and also, redirect you to. I have a very good colleague. Maybe you know her by name. There are two, Marielle Gosset and another one from Toulouse, Manuel Agrippa, and they are really experts of small reservoirs in arid regions. So they know the SWOT data very well. So we can envision like doing something together. Or, yes, very, very good there.
But also we have some tropical regions as well. I mean,
yes.
So in fact, we are now working in a lagunar system, in a tropical lagunar system, and I think some of these analysis that you are doing could be done also in this system. So yes, I think there are some opportunities. Thank you very much.
Yes. Thank you.
Well, I have an additional question for you, Fabrice.
Yes.
Recently, we saw news from Brazil that there were happening some floods in the southern part of Brazil. And the question is that if we can use these tools for early warning or creating some indexes for flooding susceptibility or severity. How can you see that?
There is two things. So we have made actually the use of SWOT, not as an early warning. I will come back on that later, just to see if we could map the extent of the flood and the water level. I didn't put the picture here, and we compared that with other techniques such as the Sentinel-2 water extent. And SWOT is doing very well actually. There is a problem with SWOT, which is called dark water. And dark water is when the water is very flat, and then the signal is not returned to the antenna. It's going away. So the water is dark. It doesn't see the water level. So this is something that we really discovered during this flood. Nevertheless, over the river and the flood itself, many places where SWOT was able to characterize very well the water level evolution during the flood. Then to create an early warning, this is something I should have mentioned, is that after 30 years of development of science, like the space agency, they are trying to develop like operational hydrology, meaning that we could use this altimetry, this extent, to characterize or observe in almost near real time or real time, like the what is happening, the extreme or the catastrophe, which are like that, and even build models that can give early warnings. One of the major drawbacks for that is the latency time of the satellite data. Meaning that if you want to do that, you really need the satellite to provide you the data almost real time or within an hour, you see? And the satellites we are using, they are not designed for that yet. So this is something that Sentinel-2 is doing, but the altimeter, SWOT, the latency time is always above a day for the moment. We are trying to push to get 6 hours, but you know that since the satellites are not made for that, we need to demonstrate the capabilities of this. But that's a very good question, and the next generation of satellites, such as this, they will probably enter the phase of operational hydrology for early warning for risk. And they're already planning a satellite which is called SMASH, which will be a constellation of altimeter that would provide water level every day, but with a latency time of a few hours. So yeah, that's very important. That's a very good point. But for the moment, we're a little bit limited by this aspect.
Thank you, but it's good to know that hydrology is moving on that direction. Yeah. Well, I don't see any additional questions. Just Alessandra Castillo says thank you for the interesting conversation.
Thank you very much to you also.
So I think we can finish this session for the seminar. We thank again all participants. Gracias a todos por su asistencia. And Fabrice, I might ask you if you could stay for a bit so we can talk
Yes, okay.
more.
I don't have a lot of time because it's 4:15 in Brazil. Maybe if you want, we can do another just talk together soon. Like we can because I'm a little bit in a rush now. So it depends. Like otherwise we can exchange by email, or then we can call each other soon in the coming weeks or something like that. What do you think?
Great.
Like
Yes,
don't
there's no
hesitate.
problem.
Yes, you can send me emails, and then we can you can plan a Zoom again, just some of us if you want to discuss some stuff. Okay. I'm sorry,
Great.
but I have another commitment now in 3 minutes actually.
Great. We will get in touch with you again
Okay.
later. And
Perfect,
thank you again.
But thank you very
And
much
thank
to
you.
everyone, and it was a pleasure to make this discussion. Thank you very much.
Thanks, Fabrice.
Thank you. Let's keep in touch.
Bye-bye.
Bye bye. Bye bye.
Bye.